Chapter 3 is on exponential and logarithmic functions. So in section 3.2, we're going to introduce logarithmic functions. Okay, so the definition of a logarithmic function is for x greater than 0, and a is greater than 0 when a is not equal to 1, y equals log base a of x, if and only if a to the y equals x. Okay, so basically logarithmic and exponential functions are inverses of each other. A is greater than 0, just like on the exponential functions, the base had to be positive, and the base cannot be 1 because that doesn't make any sense. It would be constant. And the other thing is that this argument must also be positive. Okay, and you should be mindful of that because that often produces extraneous solutions. Okay, so on the right, it says logarithmic form, exponential form. We're just going to rearrange this from logarithmic to exponential form. The little number is always the base. It always equals to the exponent. So if I rewrite this in exponential form, this is saying a to the c equals b. And these are identical statements. It's just sometimes easier to work with one form versus the other. Okay, for the next one, the base is 2 equals the exponent, and then the argument goes on the side. If there's no base indicated, this is called the common base. The common base has a base of 10, just like our number system. Okay, and then the other log that doesn't indicate its base is the natural log. ln is the natural log. The base for natural log is e. So this would be e to the 1.6 equals 5. Natural log is used in science a lot. Okay, so for example 1, we're going to evaluate these logs mentally. If you cannot do them mentally, I can show you how to do them algebraically. But for a lot of them, you should be able to do it mentally. Okay, the base is 5. You want to figure out what is the exponent so that 5 to the something will give me 125. 5 to the third gives me 125. Okay, next one, same idea. The base is 2. So 2 to the what will give me 32. 2 to the fifth. Okay, for the next one, it's a common log, which means base 10. You don't have to write the base is 10. It is 10. Okay, now let's see. 10 to the something to give me 1 over 100. So 10 to the second power gives me 100. In order to get 1 over 100, I make it negative 2. The negative moves it to the denominator. I'm going to keep going. The base is 3. Okay, 3 to the something to get 1/3. 3 to the first power gives me 3. So 3 to the negative 1 gives me 1/3. Okay, 7 to the something has to give me 1. 7 to the 0 equals 1. The log base anything of 1 is always 0. Okay, let's keep going. It says log base x. So x to the something equals x to the fourth. Well, obviously x to the fourth equals x to the fourth. Okay, let's see. The log base 3 to the something gives me negative 9. It's not 2 because 3 squared is 9. It's not negative 2 because 3 to the negative 2 just makes it 1/9. This does not exist. There is no solution. No matter what, if I have a positive base, I will never get a negative argument. This also disrespects the domain of a logarithmic function because this should be a positive number in here. Okay, now the last ones are going to test your exponent knowledge. Okay, so this is going to say 25 to the something is going to equal to 5. Okay, it's getting smaller, so I'm doing some kind of root here. Okay, so if I think about what am I doing to 25 to get 5, I'm square rooting it. If I'm rooting it, I'm getting a fraction. Since I'm square rooting it, the fraction is going to be 1/2. Raising it to the 1/2 is the same as a square root. Okay, if you are very uncomfortable doing that in your head, you could also do this by using the one-to-one property. If I rewrite log base 25 of 5 equals, let's say, x in exponential form, I would get 25 to the x equals 5. If I rewrite it with the change of base, 5 to the 2x equals 5 to the 1. Now it's 1 to 1. 2x equals 1. I get x equals 1/2, and that's the same answer I got by doing it in my head. Okay, so if you want to do the work on the side, go ahead and do it. If you do it in your head, that's great too. Okay, log base 8 of 2. So I'm doing 8 to the something to get 2. It's getting smaller, so I'm doing some kind of root on it. I'm actually doing a third root. Third root of 8 is 2. The third root is represented by the exponent 1/3. So if you would like to do it in your head, you're welcome to do it in your head. Again, if you don't like to do it in your head, 8 to the x equals 2. 8 is 2 to the 3x. And then I would have 3x equals 1, and I would still get x is 1/3. So my missing exponent is 1/3. Okay, for the last one, again, if you feel comfortable doing it in your head, you're welcome to do so. If not, you might want to write it out. Okay, 9 to the something is going to give me 27. Okay, that one's a little trickier. How would I get 27 from 9? I would actually square root it and get 3, and then I would raise it to the third power. Okay, so I would square root it and raise it to the third power. That's how I would do it in my head. This one you might not want to do in your head. If you want to do it the long way, 9 to the something equals 27. 3 to the 2x equals 3 to the third. 2x equals 3. X equals 3/2, so it would equal to 3/2 that way as well. For example 2, we're going to solve using the one-to-one property of logarithms. So for A, it says log base 3 of 5x plus 1 equals log base 3 of 13. Since the log base 3 of this equals the log base 3 of that, it must be true that their arguments are equal to each other since they are both log base 3. So I could say that 5x plus 1 equals 13. Okay, I did not cancel the logs. It's just that because the logs are equal, their arguments must also be equal. Okay, if I solve this, 5x equals 12, x equals 12/5. Okay, if in the past you might have checked this completely, I just need to eyeball it and make sure it doesn't disrespect the domain of the log function. If I plug 12/5 into here, I'm going to get some kind of positive answer. Since it's a positive argument, then this is a valid answer. Okay, I'm going to do the same thing on the next one. It says the log of x squared plus 3 equals the log of 4x. Since their logs equal to each other, then it must be true that their arguments are equal to each other. Yeah, I'm going to put this in standard form so I can factor it. Okay, I got x is 3 and 1. Again, you don't have to really check it, but you should just look back up and make sure that the arguments are positive. If I plug this in, if I plug a 3 in here, 3 squared plus 3, that's positive. If I plug 1 in, 1 squared plus 3 is positive. If I plug in 3 here, I get a positive. If I plug in a 1 here, I also get a positive. So all of the answers should work. Okay, I'm going to do one more with the one-to-one property. Okay, again, log base 5 of x plus 3 equals the log base 5 of 3x plus 13. Because the logs are equal to each other, then their arguments must be equal to each other. Okay, I got x equals -5. Okay, and then I'm just going to glance up and make sure that it doesn't make any of the arguments negative. Okay, let's see. If I plug -5 in here, -5 plus 3 is going to give me -2, which is actually a negative argument. So this answer is not going to work. I can't get a negative argument there. Since it was my only answer, there must be no solution. Okay, and this answer was invalid not just because it was negative, it's because it made the argument negative. If this had been x is -1, it would have kept a positive argument and it still would have been able to be a valid answer. Okay, next we are going to consider the graph of logarithmic functions. Before we start considering the graph of the log all by itself, I'm going to consider the exponential graph because I do know they are inverses of each other, so I can kind of see how they relate to each other. So first, I'm going to graph f of x equals 2 to the x. Okay, let's see. Let's see, I could graph 0, 1, 1, 2. If I wanted one more, I could do maybe 2, 4. I can get a good graph this way. So this is my graph of f of x. Okay, the domain of f of x is negative infinity to infinity. The range is 0 to infinity because it doesn't cross that asymptote. The y-intercept is 0, 1. There's no x-intercepts. And the asymptote was at y is not 1, at 0. Okay, before I even graph g of x, which is log base 2 of x, I'm going to actually fill in the domain, range, intercept, etc. without knowing any information. Because these are inverses of each other, their domain and ranges should switch. So the range of f of x was 0 to infinity, so the domain of g of x should be 0 to infinity. The range should be negative infinity to infinity because the domain and ranges are switching. Since the intercept of f of x was 0, 1, if I switch the x and y, the intercept of log should actually be 1, 0. And since there's an asymptote at y equals 0 on the exponential function, there's actually an asymptote at x equals 0 on this function. Okay, I'm going to go ahead and graph that asymptote in. I should probably graph the exponential one as well. Okay, I'm going to make a table to make a quick graph of this. I normally, if I pick the right 2 points, I can kind of kill this. Okay, first, I normally pick 1 for my x value. Why do I pick 1? Because the log base 2 of 1 is 2 to the something gives me 1, 2 to the 0. So automatically I have 1, 0, which is the x-intercept I was expecting that I already listed down. Okay, because this function is base 2, I'm going to pick an x that works with base 2. Okay, the log base 2 of 2 is 1 because 2 to the 1 is 2. So if I graph 2, 1, that's actually 2 good points for this graph. Okay, I'm going to respect my asymptote. And I'm going to sketch the graph going up this way. That's the logarithmic graph. Okay, these are inverses of each other. If I sketch the y equals x line of symmetry, they do appear to be symmetric. But if you ever blank out on one graph versus the other, if you can imagine one, you can flip the information and figure out the other one. Okay, I'm going to graph these logarithmic functions. I'm going to label 2 points on the graph, include my asymptote, and then I'm going to kind of consider the transformations and consider some easy points depending on the base. Okay, I'm going to start with the asymptote because that helps me know which way it's going to go. Okay, this is just x, it's not moving right, left, so the asymptote's going to be at x equals 0. So I'm going to go ahead and sketch it. You don't have to write what it is because it doesn't ask me to. Okay, now I just need 2 easy points. Okay, so I normally start with 1. Log base 5 of 1 is 0, which means 1, 0 is a point on my graph. Okay, because this is log base 5, I want to pick a number that works with log base 5. So I'm going to use 5. So if I plug in x as 5, the log base 5 of 5 is 1, which means 5, 1 is also on my graph. Okay. That's not much, but because I know the asymptote is going this way, and I know that the graph appears to be increasing this way, that's enough for me to get a decent sketch. And as long as I have those 2 points and I'm respecting the asymptote, that's a good graph. Okay, for b, it's log base 3 of x. Okay, again, there was no translation, so the asymptote does stay at x equals 0. I'm going to go ahead and start with that. It gives me an idea of how to do my graph. Easy points, I'm going to plug in x as 1. The log base 3 of 1 is 0. So 1, 0 is on my graph. Because this function is base 3, I'm going to plug in x as 3 because the log base 3 of 3 is 1. So 3, 1 is on my graph. Okay, let me label these because I told you to label them. 3, 1. Those 2 points are enough to give me a good idea of what's happening. Okay, it's going down along the vertical asymptote, and then it's going to head up that way. Okay, now we're going to consider some transformations to these graphs. Okay, C says f of x equals 2 plus log base 3 of x. First, I'm going to consider my asymptote. Okay, it's normally at x equals 0. It moves up 2, but it doesn't make a difference if I'm at x equals 0. Okay, then I'm going to consider my easiest points. Okay, if I plug in 1, log base 3 of 1 is 0. Okay, so if I was at 1, 0, normally that would be great, but now it's going to go up 2 more spaces. So instead of being at 1, 0, if I move up 2, now I'm at 1, 2. Okay, my other easy point would be 3. X is 3 because this is base 3. So the log base 3 of 3 is 1. If I move up 2, now it's up here. So now I'm at 3, 3. And again, that's still enough points. It's still heading towards my asymptote and it's curving this way. Okay, for D, log base 3 of x plus 6, this is shifting. This is going left 6. Okay, so if my asymptote's normally at x equals 0, instead it's going to move to x equals negative 6. Some people also like to set this equal to 0, and then they can solve for the asymptote that way. It's up to you. You don't have to show work, but just find a way to work for it to work. Okay, now let me consider my easy points. Okay, normally I do 1, 0. It would be here, but I want to move left 6. 1, 2, 3, 4, 5, 6, which would make it right here. Or I could consider 1, 0 from the asymptote. Okay, since this is base 3, 3, 1 is a good point, but I'm going to move that left 6. 1, 2, 3, 4, 5, 6, which would be here. Or I can consider this my new home. And if I went 3, 1 from my new home, it would go there. Okay, either way, the shape of my graph is still going to be logarithmic. Okay, I'm going to go back and label those 2 points, negative 5, 0, and negative 3, 1. Okay, let's keep going. Let's consider this one. Let's see, log base 3 of negative x. So the x is changing sign. Since the x is changing sign, this is going to reflect the y-axis. If I reflect the y-axis, that does not affect my asymptote, which is at x equals 0. Okay, I'm going to consider my easy points. I normally do 1, 0, but I want to reflect the y-axis. So instead of 1, 0, I'm going to put it over here at negative 1, 0. Okay, since this is base 3, 3, 1 is normally a nice point on my graph. If I reflect the y-axis, now it's going to be negative 3, 1. Okay, and that is good enough for a graph. Okay, and then the last one's going to have a lot of stuff going on. Okay, let me first consider my asymptote. Okay, x minus 2, the asymptote's going right 2. So at x equals 2, I'm going to go ahead and put my asymptote. Okay, and then let me think about all the things going on. Okay, so there's a negative in the front. So that's going to reflect the x-axis. Parentheses, it's going to go right 2. And then it's also going to go down 1. Okay, the order does matter a little bit. Normally you should reflect first. If you move right and then reflect, it won't affect it. But if you move down and then try to reflect, it's going to go crazy. I'll show you how to check your answer if things go crazy. Okay, let me see if I can figure this out. Okay, normally I use 1, 0. Okay, I'm going to reflect the x-axis. Oh, I stay here. I'm going to go right 2. 1, 2. I'm going to go down 1. And I'm going to use this as one of my points. Okay, let me consider my next point. I normally use 3, 1 because the base is 3. Okay, I'm going to reflect the x-axis, which is going to take me to here. And then I'm going to go right 2. 1, 2, and I'm going to go down 1, which is going to take me to here. 5, negative 2, even though I kind of crashed into my graph. Okay, I'm going to go ahead and sketch this. Okay, and because this one was had a lot going on, I might want to check my points So if I plugged in x is 3, 3 minus 2 minus 1, what would I get? I would get 0 minus 1. I got -1. So that matched my point. Let me check my 5, -2 point, because that one was a bit of a mess. Okay, if I plug in 5, negative log base 3 of 3 minus 1. Log base 3 of 3 is 1, so -1 minus 1 is -2. Okay, so that worked. That other point was also accurate for my equation.